Yes, thank you. Can you see my screen?
Yes.
All right, so yeah, I can start. Hello, everyone. I'm Mike, and I'm very happy that I can present a few of our stability investigations today. And yeah, first, let's start with the motivation about stability in power systems. So first, now we're talking about frequency stability, and the frequency is a global indicator if we got an equivalent between the load and the electrical power generation. And the definition is that frequency stability is related to the ability of a power system to reach and maintain a stable operating point following a severe disturbance. So what we're looking at now is that we've got a force situation in our power system, and we have a look if the power system is able to maintain a stable operating point. And that means, is the system able to maintain equilibrium of load and generation at the same time? This causes challenges in future power systems because of the transition of our power system from conventional power generation to generation by renewable energy sources. We've got high gradients in the generation, and so we need to find solutions for these highly volatile in-feeds. So in this part of the presentation, I would like to show one possible solution, and to answer the question, which role does hydropower play in a future power system? And to calculate the frequency stability and to make some investigations, we follow the structure we can find on the right-hand side. And we would like to answer the question, what advantages do flexible hydraulic power plants offer in terms of frequency stability? And we would like to make a determination of future flexibility requirements for hydraulic power plants with regard to frequency stability. So as you can see on the right-hand side, to make some stability investigations, we need a few input parameters. And one of these parameters is, of course, the grid model. We need the loads and the generators, and we need a severe disturbance. And the first step of the simulation is that we have to make a steady state initialization. So at first, we take our in-feeds, we take our loads, and initialize them through the power flow which we can find in the grid. And based on this power flow result we can get from the first step, we go to the next step. So we got all our values and our results in a steady state, and from this point on we go to the time domain. So in time domain we would like to simulate the behavior of the grids, the feeders and the load in case of a disturbance. And what we can find as a result of the simulation is the time series of frequency for each node in the grid, and we can evaluate the rate of frequency deviation. So yeah, starting from this point, from this structure for the simulation, we had to make a few improvements for the HydroFlex project. So at first we needed to make some improvements to the Nordic grid model, and we needed to make a detailed modeling of hydropower plants. And starting with this, we made the dynamic simulation for detailed analysis for special reference cases. So we took out a few special reference sites with a special parameterization. And starting from this, we make a determination of future flexibility requirements with regard to frequency stability. And to show different steps in an overview with the different equipment we have in our power system, we start with the differential algebraic system in a mathematical way. And there we can find some algebraic equations and some differential equations about hydropower plants, steam power plants, loads, and renewable energy sources. So we can all, we can display them all by different mathematical descriptions, and they're all connected to the electrical grid. In this case, the electrical grid is just represented by algebraic equations. And by this, we go to the steady state initialization, which I presented before. And then in the next step, we have the time domain simulation, as I already said before. But the new part in this is are the different models you can see below. And so for the conventional power plants based on fossil powers, we've got the so-called TGOF1 model, which has got a speed control and time delay of valve for which is of great importance. Then for the loads, we use an exponential model, which has an active power consumption of the loads depending on the frequency. So in this part, we can already see, okay, the frequency and its changes has got an impact to the load, and it goes back to the stability itself. And the power plants, which are connected to the grid via converters, so the renewable energy sources like PV or wind power plants, are just displayed without a frequency control loop, just to have a few to get the focus on the hydropower plants. And when it comes to develop the model for hydropower plants or for synchronous generators in general, it is important to develop a prime mover model. On the right-hand side, you can see the model of a synchronous generator, which is for a hydraulic power plant and its connection to the grid. And the part we're focusing on in this case is the one in the yellow box. So as you can see, it's a turbine, it's a governor, and we also got the physical conditions of the power plant setup. As I said before, the high gradients in the feed-in by renewable energy sources makes short-term simulations necessary. And therefore, we also need adequate models for the short-term transient behavior of the relevant equipment. And in case of hydropower plants, we got a controllable governor and the generator and exciter characteristics, which is also added by physical conditions of the power plant setup. So as you can already see by the scheme on the right-hand side, they differ in waterway and turbine characteristics and also in governor parameters. So for the next slides, there's a focus on the governor, which is different from hydropower plant to hydropower plant. And we got the turbine, which is also characterized by the conditions by the penstock, for example. So if we have a look at the governor model, you can see the governor model we used within the HydroFlex project on the right-hand side. And as I said, the dynamic behavior of the valve, for example, for steam turbines, or the gate position when it comes to water turbines, depends on different time constants. And this is, for example, what you can see on the right-hand side when you have a look at the boxes left of on the left-hand side of the gate output. So you can see there's, for example, a time constant called TG or TP, which characterizes these different time constants for the gate, for example. And in general, there are many different models for governors available in system studies in literature. And we used this model in collaboration with a few partners, which actually have a few water power plants in Scandinavia. And as you can see here, on the right-hand side, the variation of the gate position, which is in the green box, depends on the speed variation, which is an input on the top right side, so the omega, and on the power variation, which is shown on the lower right side, the PE. And so yes, if we got the different parts of this governor model, we've got different tasks they have to go through. So when we start with the PI element, just on the right of the reference speed of the generator, this one is there for proportional and integrating gain. We got the PT1 element, as I said before, it's for the gate opening. It also has got some time delays in it. We got on the lower part on the scheme, the virtual switch, so which enables the variation in the closed loop. So we can just make a back coupling of the PI element going to the input side, or we can use the electrical power, as I said before. And when we look at the speed, the generator speed, which is an input parameter of this model, we're able to compensate the changes in the speed, and it has got a mostly differentiating behavior in this case. So now let's have a look at the turbine model. There are actually many different parts you can have a look at, different aspects of models, and the dynamic behavior of turbines depends on the inertia and the compressibility of water and the elasticity of the wall of penstocks. And as you can see, it can get very complicated. And yeah, depending on the complexity of the different models, you can have a look in literature, and you can have a look which one suits the best for your actually investigations you want to make. And so, for example, the linear models, which is one of the major groups of the models for the turbines, is only suitable for small stability investigations. And in this case, small stability investigations means that you only got small variations between the load and the generations, so just small variations in frequency. But in this case, we want to have a look at severe disturbances in the grid. So in this case, we have a look at the nonlinear models. And because we don't have so many data available that we can have a look at the elasticity of the wall of the penstocks, or for example, of the compressibility of the water, we have a look at nonlinear models containing an inelastic water column. And the concept is that we've got a nonlinear relationship between the relative gate position and the fluid flow and mechanical turbine power. So you can see this model on the lower right-hand side here. And you can see different components. So we got an offset of the turbine power, This is actually the one called the PMAC in this side. And we got the no-load flow, which is the UNL. We got the H0. This is the stationary head of the water column. Yes, we have got the gate position, which comes actually from the governor model. And we got time delays of the water itself. And as I said before, because we're having a look at the inelastic water column model, we are neglecting traveling waves, the surge tank, for example, or frictional losses in the penstock. Yes, so this is to show it much clearer, I guess. So we can see we've got offset of turbine power here, the water starting time, and the relative valve position, which is multiplied by a proportional factor, in this case by a gain. And so using these models, we made some investigations. We made many investigations for the future Nordic grid. But we could see, because of all the rotating masses, the many synchronous generators which are used within the hydropower plants, there are no actual problems which can occur in the future. So we said, okay, let's go one step further. Let's have a look at the flexibility we actually could provide if we wanted to. And so we wrote a paper which actually uses the synchronous generator of turbines, of water power plants, in combination with a full-scale converter to make a feed into the grid. And actually, when a fault occurs in the power system, we got the rotating mass of the different generators, which provides inertia. And this inertia is provided intrinsically because of the physical conditions of the water turbines and the synchronous generator. And this actually makes the rate of change of frequency much smaller than like it was in the system when you don't have any rotating masses, when you just take your synchronous generators away and replace them by renewable energy sources, which are only connected to the grid by converters, because they don't have this this physical connection to the grid just as generators have. And so in the case of the fault, when you have a look at the synchronous generator, and you can see, for example, there is one power plant going out of the grid. You got the inequilibrium between the energy production and consumption in the grid. So that means there is some difference between these two values, and you need to get them back to their equilibrium. And in this case, the energy needed, the difference which you can find in the grid, is drawn from the generator's speed. And so you can see that the frequency in the grid is just going down. And it only goes down in the manner of the physical conditions, but you can go even further than this. So the idea was to emulate virtual inertia in case of a fault by using a full-scale converter. And by this, we wanted to have a look if we can reduce the rate of change of frequency in case of a severe fault, and the maximum frequency deviation in case of grid faults, if we can just reduce them. And as you can see on the right-hand side, you've got the hydromechanical setup. On the left side, as you can see, it is unchanged, but it is extended. Yeah, and you can see that here two inverters with the DC loop. And by this, we want to try to draw more energy from the rotor, from the rotating mass, then we actually would get, in case of the direct coupling of the generator to the grid. And as I already said, we made a publication about this. And yeah, unfortunately, we can't present our results in Vienna in November this year, because it has been postponed to next November in 2021. But I'm very happy to present a few of our results today. So yes, so actually, which changes have been made to the model, and yeah, to emulate visual inertia, we got still the rotating mass of the synchronous generator, because it actually provides the energy we need to provide it to the grid. We got the turbine generator unit with the dynamic behavior as modeled before. And in this case, we make the assumption that the full-scale converter has got no losses, so it's an ideal one. And we've got a control loop for virtual inertia emulation, which you can see on the first scheme on the right-hand side. So, and if we have a further look at the control loop, I can first show you the primary ideas we got. So we want to provide virtual inertia depending on the rate of change of frequency, depending on the actual grid frequency, and on the grid frequency deviation. And you can find these two parts in the control loop presented on the right lower hand side. And so the first part is the one about over the rotating mass, the synchronous machine, and it represents the energy which would be drawn from the generator, like it would be provided intrinsically. And then, if we have a look at the red box, we can find the two parts which have to fulfill the two jobs I presented. And so for the first one, we got the grid frequency, and we take its deviation over time within a depth band. And if it's outside this depth band, we use a gain to have a part which actually takes the grid frequency deviation to provide a reference power. And for the second one, we use the actual grid frequency deviation. And with the depth band, we also have a gain in this case to provide another reference power. So, and as you can see at the summation of these three different reference powers, we got one reference power which is given to the converter. And as in this case, the converter is ideal, we got the electrical power output, which actually is the reference power we got from the three different parts. So one from the synchronous machine, one from the deviation of the rate of change of frequency, and from the frequency deviation in stationary result. So this actually should lead to a lower rate of change of frequency and to lower maximum deviations. And this functionality has to be tested. And I would like to present it on the IEEE 39 bus system, which is also called New England system. And for the testing purposes, I used the 10 generators given by this exemplationary system, and I used, of course, 10 hydropower plants, and it contains also 18 loads. And the question I want to answer in this case is, can virtual inertia emulation help reducing frequency deviations in case of grid fault? So for the investigations, I made a rise of active power consumption at the part of load X shown in the grid on the right-hand side at 0.5 seconds by 50%. So we got a severe disturbance in this case. And as you can see, we got an inequilibrium because of the higher load. And this causes a frequency drop, which needs to be stopped by the generators we've got in the system. And after 1 second, we clear this fault. And we have got now 2 scenarios which have to be compared. And in the first case, all hydropower plants are synchronously coupled to the grid. So just like its system as it is today. And the second one is we have a look at the hydropower plants, which are all coupled to the grid via full-scale converters. And they also use the virtual inertia emulation control loop. So we can see the results on in these 2 graphs. And as we can see, at first, if we have a look at the case that we have no virtual inertia emulation and all the generators are coupled synchronously to the grid, we can see that when the fault comes in after 0.5 seconds, we got some frequency deviation, which go down to, in this case, I have to say only 0.996 per unit. So it's 0.996 times 50 Hertz in this case. And if we have a look after the fault is cleared, we can see the grid frequency just recovers very slowly. So you can see after 5 seconds, we got only this this very small recovering in this case. And then if we have a look at the grid when we use all the generators coupled to the grid via full-scale converters and the virtual inertia emulation, we can see that we only have a few small dip at 0.5 seconds, which goes down to 0.999, for example, approximately 0.999. And after the fault is cleared, we got another dip because the control loop needs to react on this load, which is set down to 100% again. And as you can see, we got no frequency deviations after the fault is cleared from the grid. So there's actually no recovery time which has to be applied to the grid to fully recover from this fault. So you can see from the first dip, we got a similar rate of change of frequency, but we got a much lower maximum frequency deviations in case we use the virtual inertia emulation. And if you want to have a look what happens just behind the full-scale converter from the grid view, we can see that in case that we have got the generator synchronously coupled to the grid, that the rotor speed approximately is the same as the frequency at this node, which is clear because the generator speed actually defines the frequency at one certain node. But if we don't have this synchronous coupling between the generator and the grid, and we have a look at the full-scale converter, we can see that the frequency and the actual rotor speed can have bigger deviations. And this is because we draw much more energy from our rotor when we use the virtual inertia emulation, with the effect that we can hold our frequency at almost a constant level of 50 Hertz, but at the cost of the loss of some speed of the generator. But as we can see, after the fault is cleared, we have a very good recovering of the rotor speed if the fault is cleared then. So if we have a look at the test system, we can draw the conclusion that it's the concept of virtual inertia emulation works for a test system. So in the next step, we wanted to apply it to the nodal transmission grid. And in this case, we used the grid model. We also used for a few of the market simulations. And in this case, we got approximately 1,000 water power plants, about 30 gas turbines, and 1,000 loads with the standard parameterization. And in this case, we have a look at the same scenarios as we had in the test case. And in this case, we also investigated fault situations with a lack of power in feed. So, and in this case, we had a look at one node, which was near Oslo, and we had a look at the frequency and at the rotor speed of a generator, which was connected to this node. And in this case, we can see very similar results compared to the ones in the test system. So in this case, we got also our dip at 0.5 and 1.5 seconds. And we can see without virtual inertia emulation, we got a few deviations of the frequency within the dynamic case. So after just 0.5 seconds, for example, and we can see after 5 seconds, we still have some deviations in our frequency. And what is different in this case? It's different that the depth of the dip is approximately twice as high in the case of the synchronously coupled generators, because we can see we got a dip down to 0.995 in case of the in the case without virtual inertia emulation. And if we use the virtual inertia emulation, we got only half of this deviation. So in this case, we can also see beneath the fact that we don't have a stationary frequency deviation after the fault is cleared, we also have a lower rate of change of frequency in this case. And in this case, it's decreased by 50%. And on the right-hand side, we can see a very similar picture to the one we've seen in the test system. So we can see we've got drawn much more energy in case of the virtual inertia emulation from our rotor. So the rotor speed is lower after the fault is cleared, but we can also see it is recovering, and it has to it will be back to its initial state after approximately 15 seconds in this case. So we can see in this case the virtual inertia emulation enables the possibility to decrease the rate of change of frequency on one hand side, and on the other hand side the frequency nadir after grid fault, causing an imbalance between the electrical energy production and the electrical energy load. So yeah, that's it from my side. Thank you for your attention, and I would be happy to answer a few questions.
Thank you, Mike. So we'll open up for questions.
Hello, my name is Lynn Saren, and I have a question. When you use this virtual inertia, how did you model the turbine? Because my worry would be that if you decrease the speed on the rotating side, that you would maybe lose more power from the prime mover because you went to a non-optimal speed. So did you consider this, or what are your thoughts on that?
Yes, so the turbine is modeled, but primary energy, so the water which is actually flowing through the turbine, is considered as a constant. So this is why we got always this recovering, because we don't need to worry about the actual mechanical power coming from the water in this case. Is this the question you had, or did I get it wrong?
Yeah, my question was because typically I think you would lose efficiency when you change the speed of the turbine because it's running on the optimal speed normally, or maybe you would lose in one direction and gain in one direction depending on exactly, especially I mean if it's a Kaplan turbine, for example.
Yeah. Yeah. Okay. That's
so
yeah,
like
now I get it.
the effect on the change of speed, because you would change the speed much more on the turbine side than you would in a normal frequency deviation. So I was wondering how that would impact if you would sort of come into bad areas with regards to rotational speed of the turbine and maybe lose have problem coming back to, for example, to nominal speed and so on.
Yes, this might be a problem, but actually the efficiency was not one of the points I considered in this case.
We have a question in the chat room as well, or Niklas, I don't know if you want to pose it yourself.
Yeah, I wonder how much the generator output increase in the second where you are active taking out the energy.
Yeah, that's a very good question. I don't have slides with the active power generation in this part. I guess it was a raise about I guess 30%, because it got limitations as well. So it's just because we wanted to prevent the generator and the turbine from being from getting some mechanical.
Exactly, the generator is designed for a braking force that is not.
Yeah, right. Yeah, that's what I want.
The limit of the power.
Yes, yeah, it has been limited just to don't break the turbine in this case, or to get some losses because of the mechanical powers we have right there.
Any more questions to Maik's presentation?
Another question from Niklas here. That means that when you use this function, you already have putting out the unit from being automatically involved by adding inertia. So that means that when you are not having this in the grid, you don't have the same inertia from the start.
Sorry, can you repeat this?
When you use this function, you're taking out the inertia that is coupled to the grid from the beginning. So that means that you have to have having good availability of this function to show that you have a stable grid at all situations.
Yes, so the inertia I got usually when I got this synchronous coupling is also considered, but it got two additional parts. So it is just higher than it was with the synchronous coupling when I use the full scale converters.
Roberto, did you want to pose a question?
Just a moment. No, sorry. I unmuted the microphone.
That's okay. Okay, thank you very much to